And I like that. All right, 32. So nice little challenge. So number 32, in same chapter, says, okay, in 2005, this guy here, whoever he was, won the pole of the U.S. Grand Prix race fine. 133 miles per hour this guy travels. Now, I want to know his speed in centimeters per second. See, that's where I'm going. Again, we have two types of units. We got ourselves a distance, we got ourselves a time. Most everybody in here loves to do that time first. So let's just get it out of the way. All right, I'm going from hours to seconds. So in 1 hour, I've got 60 minutes. In 1 minute, I've got 60 seconds. Okay, now I'm left in miles per second. Wonderful unit of speed, just not the one we want. All right, so now we have to convert this miles to centimeters. Now, who's got a bright idea? Oh, well, look at all this, right? Now she's thinking like me. God, I've created monsters. Okay, miles to feet. So we got 1 mile here is 5,280 feet. Okay, that's gone bye-bye. Now you want to do what? Now feet to inches? Okay, so 1 foot is 12 inches. And then you want to do 1 inch is 2.54 centimeters. And I'm running out of board, right? Can we catch that? Sure we can. We can wrap the answer back around. So now, what's the only thing that's not canceled out is that centimeter per second. Lovely. That's what we got right there. All right. Now, you know, a lot of times I am sloppy when it comes to abbreviations and so forth. I get up here and get so excited. You know, but certainly the proper unit for second is a lowercase s, and of course this is cm, lowercase cm. All right, even though I've got SEC written there. Okay, so let me just bring my calculator back over here, and then that way she won't have to keep following me unless we run into major problems, and then I'll throw it back up there. 133 divided by 3,600 times 5,280. Times 12 times the 2.54, hitting the equal sign at 594. Something just don't sound right. Let me regroup. Yep, I didn't type in something right. Now we're working. 5,945. Do I have a second on this? All right, so a couple people have seconded. Right, we got a freaking business meeting going on here, right? So this right here is around 6,000 centimeters per second. Now that makes sense, right? 133 miles an hour is pretty fast. And if you're going 133 miles an hour, you would expect around 6,000 centimeters to pass you every second. All right? So I'll buy that. You guys may think I'm crazy by always stepping back and looking. All right, but you always want to be sure that it's reasonable. I've not looked in the back of the book. I don't care, but I know it's reasonable.
You just multiply this straight across.
Yes, ma'am. That's all I did. Well, no, now here I divided by 60 and divided by 60. Yeah. How are we doing? Good? Okay. Are we good to go with temperatures or not good to go with temperatures? Good to go? Sure. I don't care. Yeah. Oh, you mean and go home now and not do any more talking? Oh, no. No, you can go. Yeah, you can ask me anything you want at any time. I don't care. No. Yeah, you can come back and revisit it. I will not. But if you got a problem, yes, always come and ask me anything you want. All right, temperatures. Well, there are 3 temperature scales that are normal, okay, to talk about. There are other temperature scales, okay, but there are 3 that are used in a normal, everyday scenario. The first one that we are familiar with is, of course, the degree Fahrenheit. And that was named after Fahrenheit, naturally, right? They named the scale after him. Now, everything I'm going to be talking about from here is based on water. Okay, so where does water freeze in our Fahrenheit system? 32, and where does it boil? 212 degrees Fahrenheit. So why are these numbers crazy? Well, the reason these numbers are crazy is he calibrated his thermometer in Berlin, Germany. Of course, years and years and years ago. And he calibrated it based on the temperature in Berlin during the year he was calibrating it. All right, now you got that, right? And he wrote all of this down in a wonderful scientific paper. Well, that's the reason that there's just randomly a 32 there, because that just randomly is what happened in Germany during that random year he thought about this. Okay, but through history it's stuck. Now, there is another type of scale out there called the degrees centigrade scale. Now, that water freezes at 0 degrees centigrade and boils at 100. And as you can imagine, this scale is set on a calibration of water. Now, that's good, because maybe you guys don't understand this, but as a scientist, we like anchors. Okay? We like something that we can always refer back to. So it does not matter if you're a scientist in Africa, if you're a scientist in Mexico, United States, you got water. And if you need to whip up a thermometer, you can figure out where water freezes, where water boils, and get your thing calibrated. All right? So that's why this one is what most of the other countries use, right? So if you go to some other place and they say, you know, the temperature outside's, 28 degrees, they mean 28 degrees centigrade, not Fahrenheit. All right, we Americans just like this because, Richard Nunn, the weather guy, and everybody talks about that, right? Okay, then there's one more scale that's called the Kelvin scale. Okay, now water freezes there at 273.15 Kelvin, and it boils at 373.15 Kelvin. Take note, this is a temperature scale where a little degree sign is not used. All right, this is the absolute scale. Now, for scientific purposes, this is the scale that is most widely used. So I know somebody's going to ask me, well, if you could explain this crazy numbers, then explain these. All right, here it goes. If you take a normal gas, now some gases don't do this. For example, carbon dioxide does not do what I'm about to tell you, but most gases. What happens to water? Water's a gas, right? There's all kind of humidity out there. So if you take humidity and cool it, what does it do? Turns into a liquid. If you take liquid and cool it, what does it do? Turns into a solid. Fine. Most things out there do that. There are things that don't do that. Like there is no liquid carbon dioxide at atmospheric pressures. Okay? You can have liquid carbon dioxide, but you're going to have to tinker with your pressures. Alright, so here's what they did. They said, okay, if this is a temperature scale here, and this right here is extremely brutal cold, and this right here is extremely brutal hot, what happens whenever you cool the gas? All of a sudden the volume goes to liquid. Okay? So just pick another gas, any random gas you want, and you pick that, and you pick another random gas, and you pick another random gas. These are the curves you're getting. And all of a sudden you can measure these pressures until they turn into a liquid. All right? So then what you could do is you could take a straight edge and extract